At first glance, Bahar Towers seem to be wrapped in a frozen geometric pattern. Then the sun moves, and the pattern moves with it. Across the curved facades, enormous triangular screens deploy in one area, fold back in another, and create a slow wave of shade around two towers rising roughly 150 meters above Abu Dhabi. The buildings do not rotate. Their glass does not change color. Instead, an independent skin outside the windows follows the most relentless force in the city, the desert sun. The effect is striking, but it was not designed simply to make the skyline look futuristic. A glass office tower in Abu Dhabi faces a difficult contradiction. People inside need daylight and outward views, yet direct solar radiation can turn a transparent facade into a vast heat collector. Darker glass can reduce part of that load, but it also blocks useful daylight and can leave interiors dependent on artificial lighting. Heavy air conditioning can restore comfort, but at a major energy cost. The challenge was therefore more precise. Keep the clarity of glass while stopping the most punishing sunlight before it reaches the window. The answer began with an architectural device that had already solved a related problem at a much smaller scale. For centuries, turned wood lattice screens known as Mashrabiyas appeared on windows, balconies, and interior partitions across parts of the Islamic world. Historic examples, especially familiar from cities such as Cairo, filtered bright light, permitted ventilation, and protected privacy while allowing occupants to look outward. They were not merely decoration. Their density, depth, and geometry shaped the boundary between a hot street and a shaded room. Bahar Towers did not copy a medieval window and enlarge it. The architects at EDAS and the engineers at Arab translated its environmental logic. The old screen was close to the body, crafted from wood and connected to daily domestic life. The new screen would stand outside a modern curtain wall, operate across 26 stories, and respond to changing solar angles. The cultural reference was real, but the engineering problem was entirely contemporary. The result was a second facade covering the east, south, and west sides of the towers, where direct sunlight is most severe. More than 2,000 individual shading units form the external veil, with 1,049 installed on each tower. Every unit is built from triangular sections of PTFE-coated fiberglass mesh held by aluminum moving frames and stainless steel supports. Seen from a distance, they resemble an immense field of patterned umbrellas. Seen up close, they are machines made from joints, fabric, pins, brackets, and linear actuators. The moving skin is not attached directly to the glass. It projects outward on its own supporting structure, creating a deep buffer between the sunshade and the sealed building envelope. In places, the units extend approximately 2.8 meters from the primary structure. That distance is crucial. Shade is created before direct radiation strikes the curtain wall, while the space between screen and glass remains open to the exterior environment. Because the tower's curve, one standard module could not simply be copied thousands of times. The project required 22 geometric variations, carefully coordinated so the pattern could wrap around changing surfaces without losing its structural logic. Computational modeling helped define the angles, connections, and movement. Physical prototypes then revealed what digital geometry could not: how the fabric tensioned, how the joints behaved, and how the full assembly looked from a street, an office, and a neighboring building. The modules follow a calculated solar sequence. In the morning, the eastern side receives the strongest direct light. As the sun climbs and crosses the sky, the active zone of shading travels around the towers toward the south and then the west. The screen does not need to perform the same movement everywhere at once. Each group responds to the exposure of its part of the facade, creating the visible wave that makes the buildings appear alive. After the sun has gone, the units retract and more of the glass surface becomes visible. This is often described as a facade that thinks, but its intelligence is disciplined rather than mysterious. A computer-controlled system uses the known path of the sun and operational inputs to position the shades. Safety controls can prevent unsuitable movement when environmental conditions demand it. The spectacle is therefore the visible consequence of a quiet calculation. Solar angle, facade orientation, time, mechanical limits, and the need to maintain reliable operation day after day. Reliability was one of the project's hardest questions. A moving architectural element in a clean laboratory is one thing. A moving element suspended high above a coastal desert city must survive heat, humidity, airborne sand, salt, and wind. Full-scale and mechanical mock-ups were tested before installation. One program subjected the shading system to tens of thousands of operating cycles under severe chamber conditions, including high temperature, saturated humidity, and abrasive sand mixed with salt. Wind tunnel studies examined how the rounded towers and their external skin would respond to pressure. Those tests reveal the true nature of the innovation. The achievement was not simply making a triangular screen open and close. It was designing thousands of large, exposed mechanisms that could move in coordination without turning the building into a maintenance experiment. Every hinge, actuator, frame, and membrane had to be accessible, replaceable, and predictable. The facade had to fail safely, remain stable when inactive, and preserve the weather-tight curtain wall behind it. Inside the offices, the system changes the character of daylight. Instead of relying only on heavily tinted glass, the project could use more transparent glazing because the strongest solar radiation was intercepted outside. Direct glare becomes patterned light. The view remains possible through the mesh, while the room receives a softer and more even illumination. The project team estimated that the external shading could reduce solar gain by more than half, lowering cooling demand while also reducing dependence on artificial lighting. The difference can be understood by comparing two defensive strategies. A conventional glazed tower may treat sunlight after it has already reached the facade, using coatings, dark tinting, and mechanical cooling. Bahar Towers add a first line of defense outside the glass. The skin does not eliminate the need for modern environmental systems, but it reduces the burden placed upon them. It is a hybrid solution, passive in its purpose, mechanical in its movement, and digital in its control. The historic Mashrabiya and the modern facade should not be presented as identical technologies. Traditional screens also serve privacy, social customs, and natural ventilation in buildings with very different walls, rooms, and streets. Bahar's units primarily control solar exposure on sealed high-rise offices. Yet the connection is deeper than a borrowed pattern. Both begin with the same climatic principle. Comfort can be created by shaping light at the boundary of a building before heat dominates the interior. When the towers were completed in 2012, their computer-controlled screen received the Council on Tall Buildings and Urban Habitat's first Innovation Award. The recognition reflected more than visual novelty. Here was a tall building whose identity came directly from place. The intensity of Abu Dhabi's sun, the geometry of regional architectural traditions, and the technical capacity of contemporary engineering. The most memorable view arrives late in the day, when parts of the facade remain deployed against the western light, while other sections have already folded back. The towers appear neither fully open nor fully closed. They display the sun's position as architecture. A force that is normally invisible becomes legible across thousands of moving triangles. That is the central lesson of Al-Bahar Towers. The future of architecture does not always begin by rejecting the past. Sometimes it begins by identifying the intelligence hidden inside an old solution, separating principle from ornament, and rebuilding that principle at an entirely new scale. In Abu Dhabi, a wooden screen once made for shaded rooms became a moving skin for skyscrapers. The technology is modern, but the question it answers has belonged to the desert for centuries.